Our next speaker is going to join through Zoom.
Hello, can you hear me?
Yes, we do.
Good. Shall I share screen now?
Let me introduce Geoffrey Levermore from the United Kingdom, University of Manchester. Professor Levermore works on climate change. Now, his title of his talk is The Climate Crisis, and he is Nobel laureate in 2007. Now, the title of the information about his prize, Nobel Prize, was Man-Made Climate Change. In those days it was climate change, but now it's climate crisis. It is very well understood from the title here. He was also the reasons for his prize was man-made climate change and way of counteract such change. Now, I think we are going to learn more because it's a very important topic. It concerns not only scientists, all mankind, and even all creatures on Earth. Thank you very much. Now, it's your turn. Microphone is yours.
Well, thank you very much. And thank you for inviting me, Professor Genscher and your colleagues. And I'm perhaps wise to stay here because the COVID cases are beginning to go up in Britain. We're worrying about another wave, possibly version of COVID. But and thank you for that plugs for introduction there, Professor Genscher, talking about climate change. I'm going to talk about climate crisis, COP26 and emerging technologies that are there. I'll just see if I can. Now, we know that CO2 is rising, and this is the latest graph from NASA showing the CO2 increasing from the Mauna Loa Observatory. And we can see it rising steadily up here, and we can see the oscillation due to the fact that the land mass is mainly in the north of the globe, and it's summer and winter, and the result of vegetation. This is the actual carbon dioxide in the greenhouse effect. We've known for over 100 years that carbon dioxide is a greenhouse gas, and it acts like a blanket over the top of the atmosphere. And we can see here that a lot of it is returned back to the Earth, and a little bit does escape here. I'll talk a little bit about that later on. But basically, it's warming up the atmosphere. We've known this for quite some time. But we've now got the climate crisis. If we go as we are at present, business as usual, the world is currently on track for a 2.9 degrees C rise. And this is really serious. We want to keep it below this 1.5 of the Paris Agreement. And if countries are implemented now, they'd only cut that to 2.1 degrees C. So, and this is optimistic. And the pledges and targets that we've got are actually 2.6. So this really is a crisis. The fact that we've had COVID, and without being too glib, COVID is a much easier problem to solve than climate change. Now we can see the influence of man on the atmosphere by looking at ice cores that are taken from Antarctica. The snow falls in Antarctica and there's a slight melt, but not much. And then fresh snow falls on top. So it's building up. And you can to ice cores that go back thousands of years. And in those ice cores, if you take a slice, and this is a slice from an ice core, you see these little white things are bubbles of air. So we actually have a repository in the Antarctic of the atmosphere going back thousands of years. And we can analyze that to see how much carbon dioxide there is and other gases as well. Now, the interesting thing is that one of those gases is obviously going to be carbon dioxide. But photosynthesis has changed since the Carboniferous age when fossil fuels were formed. And there's a new C4 type of photosynthesis. So fossil fuel is the old photosynthesis, and in the new carbon cycle that's going naturally in the world, that is new photosynthesis. And the strange thing is that there's a carbon-13 isotope, which is a stable one, and it's a minute amount of the carbon in the carbon dioxide. But the old fossil fuels in the old photosynthesis takes up carbon-13 differently to the modern photosynthesis. So by analysing the ratio of carbon-13 to carbon-12, the common isotope, majority of carbon is carbon-12, we can actually detect how much fossil fuel is being put into the atmosphere. And this graph here is such an important graph. I might have shown this at the previous conference, but it is really so important. And we see here about 1770, that the carbon dioxide due to fossil fuels, which is what we are putting into the atmosphere, is increasing. I'm sorry the ratio is negative, but it shows there is a change in the amount of carbon dioxide due to fossil fuel and man's action. And the result is that we can see that the carbon dioxide is increasing. And this is due to man. And they call it the smoking gun. And from these, we can trace back, looking at the temperature and the carbon dioxide. And here's Antarctica, the top graph, and it goes back over 800,000 years. And we can see that there's the oscillation here of the temperature and also with the carbon dioxide. And they're pretty well correlated. And here we are today, it's over 400 parts per million. Some people think, well, parts per million is not a lot in the atmosphere, but it has a great effect. If you have a small amount of poison, you could say it's a minute amount, but it could kill you. And the carbon dioxide is an accelerator in the atmosphere. So once it starts increasing, the temperature starts accelerating. And here we see the global average here. And again, we haven't seen these rises in carbon dioxide and temperature for 800,000 years. Why is there that variation of the temperature and the carbon dioxide? And this is due to the Milankovitch cycles, which is due to the fact that the Earth precesses on its axis between 19 and 24,000 year period. The tilt of the Earth also changes over time, and the orbit around the Sun, the eccentricity, 100,000 years to 413,000 years. And this explains the ice ages and also the interglacials. So I don't know what's happened there. Right, sorry about that. I don't know. I probably clicked on something wrongly. The carbon-13 isotope also shows off methane. Now, methane is another greenhouse gas, and it has been predicted to go down with time. And this is because a lot of leaks from gas stations, and the oil rigs and gas rigs have been improved. So we all thought that it was going to come down, but it's now beginning to go up. And this is quite worrying because methane has a large global warming potential. It's about 30 times that of carbon dioxide, even worse. And it actually makes up 16% of the emissions. This graph for 2015. And we don't fully know why this actually occurs. It's due to possibly the fact that we have wetlands drying out. In Siberia, there might be more methane coming out. It's also due to agricultural reasons. More areas being put aside for cows. And we've got to remember that cows and sheep do actually emit methane when they're digesting grass. This is quite worrying because we've got the tipping point, and some people actually think we've gone beyond the tipping point now. And it's simply looking at stability, that can we actually keep things in order, or are we going to go on an accelerating slope of increasing temperature and carbon dioxide, which would be disastrous? And simply looking at the amount of Arctic ice since 1979 to 2020, we can see there's quite a large reduction. Now, in the Arctic, the global warming is actually increasing quite a lot, more so than the rest of the globe. Now, that ice actually reflects a lot of the sunshine. So once that is not there, the solar radiation gets that much more absorbed, and that will go into the ocean and will generally heat up the Earth. So some people actually think we're at a really serious crisis point, and we might have gone beyond the tipping point. On top of this is the urban heat island, which I'm particularly interested in at the moment, and the fact that 66% of the world population will be in urban areas by 2050. And we are generating our own heat from our cities by absorbing that solar radiation, having a lot of traffic and transport in the city centre, giving out carbon dioxide and heat, and also, of course, our air conditioning, which is going to be increasingly used as the world warms up. And we looked in Manchester, and quite recently we did some measurements, and we were quite surprised that looking around Manchester, you can see so many more of these tower blocks going up. Manchester is quite a successful city, but the growth of buildings, especially skyscrapers, has been very noticeable. And this shows our data from a number of sites in the city centre, just looking at the temperature, looking at the urban heat island intensity. The urban heat island intensity is the difference between the temperature in the city centre and the temperature out in a rural area. So it's looking at the influence of the urban heat island on the actual city centre. And we can see that generally there's a rise of the temperature here from 2017 to 2019. Okay, it drops off with COVID quite noticeably, but that is quite surprising. And if we look at a number of office blocks, we normalise that with the temperature, we can see the number of skyscrapers here correlates quite well with the urban heat island intensity here. So we can see a direct correlation between the number of large buildings and the actual urban heat island intensity. So this will be added onto the actual global warming. And some cities you can consider adding on 10 degrees C at night time, which means it's going to be very difficult for people to sleep and work in those cities. And there will be a lot more deaths due to hot summers. So what can we do about climate change and the urban heat island? We could simply ask people to be more energy efficient, so reduce their energy consumption. But I also work with buildings, and it's interesting to consider occupant behaviour in buildings, and it is complex. This is from an IEA annex, and it looks as a system, including human beings, as a feedback loop here. And the things that affect it of trying to make sure that it's energy efficient and comfort. We've got occupant behaviour, we've got movement, we've got action, and then there's the building. And then it goes back, and there's physiology, psychology, economy. And all these factors, which many of them are the human factor. The human factor is very important. Consider a simple example of a thermostat. And I took a photograph of a thermostat in a hotel. And we can see it's set to 30 degrees C. Now, this is for heating that room. And I'll simply say, for comfort reasons, who wants a room at 30 degrees C? The danger is that somebody could put it at 30 degrees C when it's very cold and then leave it there. And when it gets very warm in the room, they can simply open the window. People react very differently, and we cannot predict necessarily how they are. The simple thing is that we shouldn't really have thermostats like this, which go up to 30 degrees C. Simply design it out. And we can see that if we do have the potential of occupants varying the thermostat, and also the time over which they have their heating and also their cooling, we can go a ratio almost of 19 to 1. It's incredible how much difference there is. And this is a simple building. And when we look at low energy buildings, we're also surprised that they vary quite a lot. And we can see the worst buildings for fossil fuel gas consumption and also for electricity. The worst are the red arrows and the green arrows are the good ones. So there's even in low energy buildings quite a difference. And this reminds me that there was a Hawthorne experiment. Elton Mayo did this in the 1920s. Okay, it goes back a long time, but there's still some lessons we can learn from that. And in this factory that was manufacturing relays for telephones, they found that there was poor production. They thought it was due to lighting. So what they did, they had two control groups, one with constant lighting and the other with variable lighting. And they found that when they increased the lighting for the variable group, production went up. But it also went up for the constant lighting group, because these people were talking to each other. They were social human beings. They knew what was happening and they reacted. They also decreased the lighting level and production actually went up again, which is totally counterintuitive. You need good lighting to do miniature assembly work. But it also went up in both groups. So we have to take into account the human factor. And I saw this when I was an energy manager many years ago. We looked at 9 identical children's homes and we thought, what can we do to save energy? And basically, the savings we made doing insulation, controls, loft insulation, things like that, very difficult to work out because they're all over the place. And we can also see that there are lots of different savings there and different actual consumptions from 9 identical buildings. But we also looked at the electrical systems where we did nothing. And there we found incredible savings that easily outweighed the gas savings on the heating. And this was because the people were motivated. They knew we were doing it and they wanted to help us. And I think the human factor is very important. So when we look at planning for climate change and looking at buildings, for instance, and other things, do we assume people are going to be angels and try and reduce energy for us? Or are they going to be like the devil here and try and increase things? Well, I think to be practical, we've got to regard people, they won't necessarily save energy. And we have to be very careful for the future and assume that they're going to use the same amount of energy. And I've called this max maladaptation, because people will react perhaps badly, not as you, the designer, expect. So we have to design out things. And so max maladaptation means we assume the energy consumption per person will not reduce, but we've got new technology, low carbon and renewable energy. We can also use carbon taxes, pollution taxes with subsidies and legislation and regulation. And this is really how we've got to go forward. So how are we going to get below this crisis? Well, there is some good news. Trump has been replaced by Biden. We've got the 6th assessment report coming out from the IPCC, the Intergovernmental Panel on Climate Change. And Professor Getch was very kind to say I was one of the people of the many lead authors who shared the Nobel Prize with Al Gore for the 2007 IPCC report, which was the 4th assessment report here. And now we're coming to the 6th assessment report. And as the chairman of this has said, or the president designate, it's crucial to stopping global warming. This year's climate summit will be the world's best chance of building a cleaner, better future, greener future. Now, some of the goals for COP26 are phasing out of coal, deforestation, switch to electric vehicles, encourage renewables, carbon markets and transparency. And countries have been requested for 2030 energy targets to secure global net zero by 2050 and keep below 1.5 so we can stay stable and we don't go beyond that tipping point. Now, if we're going to reduce this rise in temperature, it means we've got to cut back on our fossil fuels. Now, although this relates to a 2 degrees C rise, it means that it's even more imperative for a 1.5 degrees C rise. And 82% of the coal has got to be left in the ground, 49% of the gas and 33% of the oil. Now, the fact is that we've got plenty of fossil fuels. If we look at 2050, they reckon we've got enough reserves of fossil fuels that will be 3 times as much as we actually want, 3 times. So we're not going to run out of fossil fuels, but we've got to reduce their amount of consumption. And if we look at China, natural gas emits 50 to 60% less carbon dioxide than coal. So China, which has 28% of the world's emissions, if they went from coal to gas, they'd save 14% of the carbon emissions into the atmosphere. And also, they've got a lot of shale gas. Now, China is doing a lot on renewables. It's doing work on nuclear. It's doing a lot of work, but things can't be changed overnight. And they've done an incredible amount in bringing people out of poverty in China. And I think that we've got to actually work with the Chinese. And I think, as Professor Genscher said, we've all as countries got to work together to solve these problems. And it's so sad that we see that international politics might be hindering this. So the aim of COP26, one of them, is to get renewables and electric cars. This electric Leaf here, I've got an electric car. It's a brilliant car. But we've got to go to renewables. Now, renewables are making quite an inroad into electricity, but we've also got to consider the amount of gas that's used, the amount of petrol and diesel that are consumed. And unfortunately, at present, we've only got 16% of the world's energy is renewable. So we've got an incredible problem. We've got to get everything over to electric by 2050, and it's got to be renewable electric. In Turkey, it has little renewable energy at the moment, but it's got potential. It's got the hydropower there at 12%, which is very good. It's also got the UK is in a similar position. We also have got little renewable, but in Turkey, there are plans to increase it. Hopefully, by COP26, the Turkish plans for achieving net zero by 2050 will be released. And in the United Kingdom, there's also work being done on renewables. But to be honest, in the United Kingdom, our carbon emissions have reduced because we import so much from China. Our heavy industry has been exported. So I don't think it can say that we're brilliant at all. It simply means that we're not manufacturing very much and not producing the carbon dioxide. But there are some future scenarios for actually getting to that net zero for the UK, which might be interesting to look at. Now, these scenarios are looking at the speed of decarbonisation on the x-axis here, and also the level of societal change going up vertically. And there are four pathways here: steady progression, system transformation, consumer transformation, and leading the way, the most optimistic here. And these are the installed electricity generation, storage, and interconnection. Now, remember, everything in 2050 is going to be from renewable electricity, or you're going to have sequestration of the carbon from any fossil fuel that's burned. And this is looking at those scenarios. But if we look at the system transformation scenario, this one relies a lot on hydrogen. And hydrogen is talked of as the fuel of the future. It's also interesting that hydrogen can be used as a refrigerant for superconducting cables. So you could have a cable with hydrogen, liquefied hydrogen in it, so that you're actually keeping it cool. And you could also use that hydrogen for a fuel in its own right. So you could have a grid with hydrogen and electricity. And this one actually produces a lot of hydrogen. Now, this is quite important in Britain because we use a lot of gas for heating. And you cannot instantly change over from a gas boiler to electric heat pump. There are quite a few problems. I won't go into it. But hydrogen might be the fuel of the future, also for aircraft and also for shipping and industry, where it's very difficult to get off from fossil fuels. Now, this hydrogen could well be generated from some of those renewable electricity by electrolysis. It doesn't necessarily have to be straight from a fossil fuel. And here's leading the way.
Geoffrey Levermore, you have 10 more minutes.
Thank you very much. And here we see less hydrogen and more electricity from the wind here. So there are those scenarios which we've got to try and achieve, which is going to cost a lot of money. And the people that are going to pay are you and me, the consumers. When people talk about a tax, a carbon tax, or a pollution tax, and the polluter pays for the pollution, who's that? It's me and it's you. So there's good renewable potential, solar potential, PV, in Turkey, far more than there is in England. And less potential for wind power, whereas in England, we do have a large potential for wind power, especially offshore. So there's potential for getting this from the solar power in the desert. If we had some solar panels, simply the size of this, that would supply the world with most of its electricity. And for Europe, it would be that one there. And for Germany, this is a German slide, it would be that small one there. So we could potentially use the Sahara Desert for this. And there could be supergrids going around the world. a bit like this. And those solar panels could also be dye-sensitized solar panels that do not get affected too much by temperature. And there are electric connectors at the moment. We are just installed in the United Kingdom a cable from Norway to Britain to use some of their hydroelectricity. And they're also talking about connecting us up to Morocco and having an interconnector, 3,800 kilometer cable route, and transmitting 3.6 gigawatts from Morocco to power about 7 million homes in the UK. And there's 10.5 gigawatts from wind and solar with 5 gigawatts of batteries. This is a proposal. And whether it gets going, we'll have to see. But one of the elements that could be very useful in these is the superconducting cable, useful for supergrids. And there's also graphene, which is a new superconducting material, especially with these twists in it. I have to mention this because it was discovered by Andre Geim and his colleague in Manchester. And we got the backup. All renewables will need backup. And again, superconducting magnets might help. And we'd also use hydrogen for storage and liquid air if we compress it with off-peak electricity. We've also got nuclear power and small nuclear reactors, which can be put up, and they're 5 years construction, and they could be up and running by 2028, and they last for about 60 years. And I think we have to think of all elements to back up this renewable, and even small U batteries, they call them, which have a very good very good fuel and how it's coated. So there's also, which Professor Genscher mentioned, fusion. And he mentioned the European one, but there's also Spark, which has come out of MIT in the States and is going to use the advanced yttrium, barium, copper oxide high temperature superconductor for the containment, or mundane things that they're just reflecting paints to keep the temperature reasonable in the room by reflecting the sunshine. And I'm using this just an example of simple technology, but we can also use the fact that we can have radiators on our roofs, which when it's sunny outside, we have something that's based on PVC, thin films, that reflect the sunshine through this window in the atmosphere for long-wave infrared radiation. So actually, when it's sunny and the sky is clear of clouds, that panel is actually looking at the cold universe, which is a very low temperature. So it can be used to supplement the air conditioning. We can use PV windows and PV skins that look very much like the fabric that they're on of the building. And we've also got perovskite quantum dots, where we can vary the bandwidth. So we can make more use of the whole of the solar radiation, the spectrum. And the fact is that there are still a lot of countries in the world where electricity demand will increase. And Africa has very little access to electricity. Most of the world is okay, but we've got to think of these countries wanting to have as much an economy as we have and to use that. So here we have down here India and Burkina Faso. Burkina Faso is one of the poorest countries in Africa. And one of my students is now the Minister of Energy there. So I know a little bit about Burkina Faso. But here we've got the United Kingdom far higher. We've got China here and Turkey here. We've got to expect these countries to say, we want the same standard of living as you've got. And we cannot deny that. So we've got to look towards energy consumption increasing. So my conclusion is, there certainly is a climate crisis. We must take steps in the next few years to stop it. And this actually will be on renewable emerging technology, including superconductors, will be a major solution. Plus, international collaboration, legislation, and taxation. And thank you. I'm sorry if I've gone slightly over time.
So now we turn to questions. Is there questions in the room? If not, I can start. I have a question for Professor Levermore. You mentioned that the source of renewable energy with fusion, where superconductors are a major key. From what I know, it is not YBCO, but REPCO, which was used at MIT. But in your talk, you mentioned YBCO. Could we go back and could we be more precise about that? Hello?
Yes, that's.
Oh, do you hear me?
Yes, I hear you.
Yeah, so it was a question about this cold fusion, where the technology of superconductivity is used, and you mentioned YBCO as a superconductor, but as far as I know, the YBCO magnet has never been used to produce. This is with REPCO.
Yes. Well.
Sorry.
I
I think okay. So this is with REPCO, not yet YBCO. I think YBCO is a bit of a dream yet.
Well, it said I just simply took this off of one of their news announcements, and they said this is what they would be using. So if you go to that website, I mean, I not being an expert on superconductivity.
So okay, so I
I
think those guys, just for everyone, is the website is probably erroneous. Like the REPCO magnet is 22 Tesla, and YBCO magnet has not been used yet. It's for the future.
Well, I think this is actually talking of the future.
Yeah.
And as with most fusion.
Let me ask you a question for you. Do you think finally, at the end of the day, we will not be dependent on a solution like this one, like the cold fusion, that will provide free energy for humanity forever with no waste? Basically, will not it be just this solution and that's it?
Well, I think we've got to spend a lot of money on research and development to make sure that we have these solutions there. Now, I'm not sure that this is cold fusion. This is ordinary fusion. And there have been some developments made in Britain on fusion as well. They've been able to use the diverter on their tokamak to actually take out the plasma at a much lower temperature, which does mean it's more feasible. You've got the European one, and you've got various things happening in the States. I think the problem with research is that suddenly you get a breakthrough. You had that many years ago in superconductivity, there was a lot of activity. And I think of lighting. When I started my career, I was doing a bit on research in lighting. And the common lamp people were using was a tungsten lamp. And then that was 10 lumens per watt. Then people were going to miniature fluorescence, which was about 55 lumens per watt. And now we've got LEDs, and that is actually going up to about 100 lumens per watt. Those incremental changes, there are sudden changes as well. And this is what we've got to be aware of, that technology, science and technology are very good servants. And rather than legislation, it's far better to invest money in science and technology. If I might just expand a little bit, I think some of the public blame some of the scientists for the fact that we're in this climate change situation. And they blame the environmental pollution on the science and engineering, which is very wrong. It's how people use it. And it's very important that we do promote science and engineering, especially amongst young people. And it's going to be one of the major planks of how we get through the climate change crisis.
Thank you. Right. So more questions for Professor Levermore. Over there. Yes.
Oh, thank you for interesting talk. It's not clear. Global transition to new energy technologies, construction new factories for energy, for new energy technologies will not produce even more CO2. Yeah, and make situation even worse now.
You're presumably referring to the fact that in making something, you use energy and you produce that carbon dioxide and other greenhouse gases.
Right now, we have a quite complicated situation. You talked about this, it's crisis, and maybe it should be smooth. It should take maybe long period, but it should not be sharp.
Well, I mean, using renewables overall is going to reduce the amount of greenhouse gas emissions. But when you look at renewables, you see that there are some environmental problems with them, that some of the chemicals you're using to produce, for instance, a solar panel or quantum dots is not environmentally good. But you have to trade off that with the stopping the greenhouse gas emissions. I think one of the things that Greta Thunberg has done well in raising the prospect of the climate crisis, but in her book, she said, I see these things very simply. I see them in black and white. Unfortunately, life is very complicated, and climate change is very complicated, and you can have unexpected consequences. One example was that we insulated lots of blocks of flats in the United Kingdom, not realizing, or perhaps ignoring, that some of these panels were actually a great fire hazard. And there was the Grenfell Tower fire, in which about 73 people died. And that was unexpected consequences. Okay, I think there was a lot of profits considered and people putting profits before lives. But we have to be cognizant of the fact that it isn't all one way. There are complications and unexpected complications. But this is life and this is progress, and we have to deal with it. If we go to more nuclear power, there's going to be more nuclear debris we have to deal with. And some people say, no, we have nothing to do with it. Germany, as Professor Gentscher's slide of nuclear reactors shows, have reduced their number of nuclear power stations after Fukushima, and for political reasons. And what are they doing instead? They're burning lignite coal, which is one of the worst polluters. It produces carbon dioxide and so much pollution. It's unbelievable. And that is totally the wrong policy, simply for the fact of political initiative and people's perception.
Thank you.
Thank you, Professor Levermore.
We are running out of time, so probably we need to. We are better stop. We better stop here. So we thank Professor Levermore for his marvelous talk. Thank you very much.
Wait a second. There is still one question from the internet.
Was it?
Yeah. Tide energy. Do you mind to comment on tide energy? Then we stop with this wonderful presentation. Thank
Yeah.
you.
Tidal
Professor
power.
Livermore, are you?
Yes.
Yeah.
Yeah. Tidal
Someone
energy.
wants you to comment on tide energy.
Yeah. Tidal energy certainly is something that is very applicable. And one of my colleagues in Manchester is doing a lot on tidal energy. And Britain itself, having a large coast, could benefit from that. But the sea is very rough, and you have to spend a lot of money in making these systems very robust. And at the moment, tidal energy is much more expensive than putting a wind turbine in the sea. You've also got barrages that could go across bays, and then you have some environmental people saying, well, a lot of migrating birds use that estuary, and if you put this barrier across to drive a turbine, it might upset their home. So these are considerations. It's certainly in the mix and it's coming up, but it would produce for Britain about 10% of the total energy requirements. And it's still at a very expensive stage compared to offshore wind turbines and even less than onshore wind turbines.
Okay, thank you very much for a very interesting presentation. And let's thank Professor Levermore.
Thank you.